Yeah. So first, thanks the organizer and for this very nice invitation. Okay, so I start. So novel results for QFT by large quantum number limits and the application to standard model physics and beyond. So here at CP3, actually, we start the project and keep asking ourselves questions. So basically, in this talk, I will categorize into a few questions step by step. So the question we ask ourselves most of the time is how to make the standard model UV complete without gravity. So I assume here everyone's familiar with standard model, and so the issue here, you can see this diagram. So here, this G1 is the hypercharge gauge coupling. It will keep growing until blow up. This is the lambda for the U1 in the standard model. And when this G1 getting blow up, and you can see all the remaining couplings will getting blow up. So this is the problem. So in that sense, standard model is not a UV complete theory because of this U1. Okay. Even the QCD SU3 is asymptotic free by itself. So then Wilson, to address this issue, he proposed a fundamental theory should have an UV fixed point. So in that sense, the coupling will stop running and it's more or less get frozen to certain energy scale and then at the fixed point. So in that sense, the standard model is not a fundamental theory because it's running to the lambda pole, as I showed in previous slide, because of this U1 gauge coupling. So there are two ways basically to realize the UV fixed point. One is people always very familiar, and starting with David Gross is the asymptotically free. David Gross and Wilczek, of course, and the Polis. So for asymptotic free, we sometimes call it a Gaussian fixed point or trivial fixed point. And that's another also very interesting kind, but it's not explored a lot, but recently it's gaining certain energy. It's the asymptotically safe. It's running to an interacting fixed point. Okay? And I do not want to go into very detail, but it's asymptotically safe. Interestingly, it's always will kind of relate to certain non-perturbative perspective. Okay, let's continue. So far, just a short reminder. So in the community without gravity, so there's only two kinds of a way to realize asymptotic safety. So the first kind is called the Venetiano limit by using that. So this is actually developed by Francesco Cennino and Littin. And so the idea is by Venetiano limit is you need a large NC and large number of flavor at the same time. And by using that, you can have asymptotic safety. However, it's very hard to connect to phenomenology because you large NC. Well, what kind of the real model in the physics has large NC, right? So then we develop the other way is by using this large 1/F techniques. And so actually, I should say this is the only way to realize asymptotic safety without gravity at the same time can connect it to phenomenology. So I think that's why actually it's an important procedure. So let's go into the detail. So 1/F expansion is first actually developed by Pascal and in QED, and Gracie is in non-abelian, and later on it's summarized by Bob Holden. He wrote a very nice summary paper of these two. Okay. Then, so basically Pascal, he noticed it's interesting. You can sum up this kind of bubble diagram. So this is the gauge line, and these solid line are the fermions. Okay, so he noticed this kind of bubble diagram you can sum up, and then interesting you can provide a closed form. Okay, so basically, so after you sum up these, it's encoded in the summation functions, and you obtain this beta functions. So here A is the Hooft-like coupling. It's the NF times the gauge coupling alpha. It's here for U1 is basically the G1 squared, that was 4 pi squared. So the very interestingly is actually this is how connected safety is. This summation function has a pole structure. So if you look into this carefully, and it has a pole at x equals 5, which corresponds to the Hooft coupling at a equals 15/2. This pole structure, it's a logarithm pole, actually provides a negative contribution in the beta functions. So that's the whole miracle inside this. So you can see certain point because of the negative contribution, and the beta functions go into negative and will reach to a UV fixed point. Of course, it's never going to the pole, but it's when it's very close to the pole. This is the pole and never close to never getting really to the pole, but it's very close to the pole, and you obtain a negative contribution and go into the UV fixed point. So basically, sorry,
one question.
Yes.
So which theory are you computing this beta function?
So far this is the very simple U1 QED, and with fermions, yes, NF number of fermions. So okay, just very simple, yes. And so you can see it's will reach to a UV fixed point. So basically, we claim very strongly, and in our paper, is this pole structure will guarantee the UV fixed point, and we generalize it into the whole standard model. That's our progress basically. So this is the picture, and actually sometimes my friend knows. So when I first obtained this diagram, and I claim this is one of my happiest moment. Because it's really a surprise. So in the end, so you can see all the stand model. This is the stand. This is the quadratic coupling. This is the Yukawa coupling, and this is all the standard model gauge coupling. So eventually, it's all going to so for this part, it's going to UV fixed point. It's interrupting safe, and the Yukawa is asymptotic free. It's a very nice picture. So I just go into a little bit more detail. We introducing, for example, you can build introducing whatever the kind of the fermions we charge under this kind of growth, right? And then it's this number for copies, MF3, NF2, and NF1. Eventually, by introducing that, because of the pole structure, first inside the gauge coupling, for this gauge coupling, you run into the UV fixed point. And then because of the gauge coupling into the fixed point, this brings the remaining coupling also going into a fixed point. So that's the feature inside. Of course, I will show later on there's a subtlety for this quadratic coupling. So, but this cannot be realized in this first paper. So let's proceed.
Another simple question. So this nice diagrams you obtained, is it in strict NF goes to infinity limit, or?
Yes, this is amazing question. No, it's actually the NF is here is roughly order of 50. So you are not less order of 50 copies. 50. So yes, you're not necessarily going to a number to infinity, because of course when you NF going to infinity, also it can be realized, but NF to infinity is never realized, never matching the never connected to the real phenomenology, because we don't care about the infinity large color or infinity number of flavor. That's it. Of course, the theory on the theory side is also interesting. I do agree. Okay. And actually,
okay, sorry.
Go ahead first.
What if I do 1/NF correction? How does it change this feature?
Yes, this is exactly I want to say. So basically, you can see the 1/NF correction is you need sufficient NF, and then it's like the 1/NF square, because so far we are doing the F1 of leading order. And basically, if you have you need sufficient large NF, then the 1/NF square contribution is suppressed. So by actually we did the estimation that for non-abelian, for them, it's basically roughly 10 times the NC. So which means when for SU3, let's say, so you need a certain number of flavors, and in that sense, the 1/NF square contribution will be suppressed compared to 1/NF. So that's why actually, because we want to connect it to phenomenology as much as possible, then we choose the NF which is close to the lower bound. So in that sense, the 1/NF square is suppressed, but at the same time, NF is not too large. But NF is a lower bound. And in any case, if just NF larger than this lower bound, it will satisfy the suppression of 1/NF square. It's the same, and later I will mention for the 1/2. It's the very similar story. Okay, let's proceed. So then the next thing is we notice actually we can generalize this large NF gauge beta function to more general. For example, the previous the Gracie has done is the simple gauge group. Now we can do the semi-simple, And then the next thing, so we realize also we can insert a bubble chain to the cortex and the recover. For a generic gauge recover system, instead of only the bubble chain previously in the standard model case, we only insert the bubble chain inside the gauge beta function instead of all the remaining. But the calculation at that time is not done. So we really developed the whole calculation. So the first one is this semi-simple gauge. So you can see here, we can notice because this gauge line and this gauge line are different now compared with. So this is the addition diagram you need to involve. So after that, you can see that the beta function for the gauge coupling now semi-simple is you have two. So this is the initial one. You have a summation function. Now you can also have another summation function. So you have two, and the remaining are basically the group part, group series structure, and this is the one of NF. Okay, so basically that's the structure of this formula. So then we also calculate for example, you can include this bubble diagram inside this Yukawa, right? And you can also include the bubble diagram inside this kind of cortex. So it's then we calculate these, and finally we actually provide a recipe. So this is actually both, I think, interesting for and important for theory and phenomenology. So now it's basically the recipe is like this. You just give me the one loop, whatever the one loop beta function you have. So for example, this Yukawa, the C alpha is the whatever the one loop result, one loop beta function you calculate, and then you basically we already arranged this it's just as a summation functions. You just using this recipe, you will have the bubble diagram improved Yukawa beta functions. So this is actually also important for phenomenology because they want to have something high loop contribution, right? And this is very easily from just input one loop, you already can get the high loop encoding this high loop information. So the other thing I want to mention is here for the Yukawa part is you also have a pole at a 12th coupling at 15/2. So this is something I will go into more detail later on. So this is for the Yukawa, okay? And for the cortex coupling, I also have the similar recipe. And all these parts are the summation functions. So the same, you just calculate the first, whatever the model you're given, and you calculate the one loop beta functions. And then by using this kind of a recipe, I can provide you the bubble diagram improved cortex beta function. So that's why actually this become a kind of important and interesting to both phenomenology and the theory. Okay.
Sorry, so is the beta function at which loop order, or it's a for loop order?
The beta function here is all these coefficients are only at one loop level. So however, this bubble of course is in infinity high loop coding. Yes.
So do you need to suppose I want to know like the one loop result, you will need to expand those integrals at one loop.
So you do not expand. It's basically you calculate the first. It's you calculate the one loop beta function. Forget about the bubble, and you will have the C alpha prime. This is the G to the fourth contribution, and you will have the G1 G square for this coefficient, just the one loop, forget about the bubble. And this coefficient will be exactly the same after you inserted the bubble. And we already arranged the recipe into like this. So, and this is basically the summation functions provided here. So you do not need to do anything else. So just calculate one loop and input it into this recipe, and it will provide the bubble diagram improved, the one loop beta functions.
Okay, so the beta function is still one loop, but it's improved by the bubble.
Exactly. Yes. Okay. So now I go to the poststruct. This is actually the most interesting, and let's see. So you can see for all the Yukawa and the cortex, we found all the summation function has the post structure at the coupling at 15/2. By the way, I should mention this for the non-abelian gauge coupling. So before I said for the U1, the pole is at A equals 15/2, the same. However, for the non-abelian gauge coupling, the pole is at A equals 3, which is smaller than 15/2. This is the very, very important piece. Okay, so you can see this is exciting. So for the Yukawa coupling, because you can see for the Yukawa, because now we have this pole contribution inside and the bubble diagram basically. So you will see that the Yukawa coupling compared with the standard model picture previously, it's slightly different. It's become asymptotic free, right? And asymptotic free even faster because of this can at a certain point when the closing to 15/2 it decreases very faster. However, for this coded coupling, this is an issue. The coded, because this is not a multiplicative proportion to lambda. So which means when if you just go into the 15/2, this coded beta function will blow up. So which means that our previous case is the diagram it's everything is right, but the coded is not right because the coded coupling actually will blow up because of this. So immediately you see how to get around this, and this is important. Is because the A15/2 is the same as the pole as the U1. However, for the non-abelian is A equals 3, which is smaller than this. So which means if in your model you do not have any U1, only have non-abelian, so then all the gauge coupling will run into fixed point at A equals 3 and the frozen, right, before 15/2, and then nothing will blow up. So this is the key. So we found that the physics inside is basically the U1 is not completely compatible with this coded coupling. It will make them blow up. However, if you in your theory you do not have U1, you only have non-abelian, it will be perfect. But to realize this is very simple because you just need to embed U1 into non-abelian. This is there are lots of grand unified type of theory is realized like this. So that's become our next motivation. So here is just a U1 Landau pole as a summary. So as I already mentioned, it's the incompatibility between this U1 and this heat self-coupling is motivate in the study of grand unified. I think this is an alternative motivation of why we need a grand unified theory. It's not just to unify this interaction, and also is to from asymptotic safety perspective, it's the first time we provide another strong motivation is we need to get rid of this U1. Okay. So the question number 2, as we ask ourselves, can we make the standard model UV self through the grand unified embedding? Then we can see, of course, we can, right? And so there are 2 ways, at least so far. Of course, there are more. You can do SO10, you can do SU, but SU5 has a proton decay issue. But for Patis-Lam safe trinification, they are totally fine. So because of time limitations, I will focus on the Patis-Lam model today. Okay. So the Patis-Lam model. So this will basically this is the gauge group SU4 times SU2 and SU2R. So actually, I should say Patis-Lam model actually is the most beautiful model to me. It's because it is very economical. There's nothing extra. So compare with SU5, there's the one thing extra is the right-handed neutrino. But this is exactly what we need because to addressing all this neutrino phenomenology, you really need the right-handed neutrino. So that's why actually it's economical and provide everything we need. Right? So to make everything simpler, of course, you can do symmetry breaking from the Patis-Lam to left and right model. This is also another very hot topic in the phenomenology part. But we made it simpler to directly break it into the standard model. Okay. So before I continue, let's just mention some feed content. So this is the standard model SU2 gauge field basically. And this is for the left right, you have SU2R, you have extra gauge field, right? And for this SU4 part field, you can so basically this G, these G are the convention, these SU3 gluons, and very interestingly, we have extra. This is the lepton quark. So it's basically the gauge interaction connected to the lepton and connected to the quarks. Okay. And automatically, you can see there are hundreds of even thousands of people playing with the U1B minus L. And it's in Patis-Lam, automatically it provides a U1B minus L. you do not need to add in extra. Right? So actually, this is a very simple economical framework and provides everything to BSM and beyond standard model physics phenomenology so far. Okay. So there are four to realize the symmetry breaking, and then there are two kind of scalar field. This is the simplest scalar sector we introduce. So the first one is the 412, it's charged on the SU4, and this is SU2R. So you can see immediately it'll break SU4 and SU2R and direct it to the standard model. And you also have this bio doublet, because this plays a role to break the electroweak symmetry breaking. So you can see why this the partition is so interesting, because this bio doublet, it's actually after partition symmetry breaking, it's become 2-Higgs doublet model. So this is the 2-Higgs doublet proposed by T. Lee, right, at the beginning. It's 40 years ago almost. So yeah, you will have the 2-Higgs doublet model. So it really provides everything you need for BSM. And here basically I list all the coupling. Okay. So just before continuing, so I just it's not necessarily going into detail, but I just want to show, I already mentioned a lot, is how there's so many advantages for this particular model. Okay. So then it's basically it's the recipe. So how to do this? So it's the same as the standard model case. Now you're introducing a copy of these three different kind of copy for this vector-like fermions. And then because you introduce these vector-like fermions, and then for the gauge coupling, and you will see the beta function now is it's a bubble diagram improved, right? This is a summation function. So this is basically it's the initial one loop result, and then you adding to this vector-like fermions into the summation functions, then you will have the bubble diagram improvement for the gauge coupling beta functions. So this is basically the procedure. And you already can expect it, because for each of them, it will go into a fixed point. They are all non-abelian, and the fixed point will at the top of the coupling A equals 3. Okay, so this is okay. So
one question.
Yes, go ahead.
You have these three new type of vector-like fermions with
yes.
large numbers. So
yes.
Are there any relations between these three numbers, or they are independent? You just
they are independent. They are independent. Actually, you can construct a more complicated models to make them related, even introducing certain symmetry beyond to make these copy. It's totally fine. But because this is the first paper, and we make it as simple as possible to show the procedure to play with this. Yeah.
So it's like a free parameter now.
Yes, exactly. So you can see when introducing this the 3 parameter, you can play. So this is the first case. For example, you can choosing this kind of copy, and you can see this is a very alternative picture of the grand unification. Because before you think of a certain point going to one single gauge group, and the coupling, all the gauge coupling needs to run into a certain point, right? And this is alternative. It's automatically they will run into together. And if you're choosing this kind of copies, and then it will merge into a fixed point. So this is an alternative picture. So of course it's that most of these you need to arrange this NF at eventually you need to match in the infrared. But here I just show a sample. Because infrared you need to, for example, matching the standard model Higgs. You need to have 125 Higgs. You need to have the top cover coupling which matching. I will go into more detail later. But this is an interesting sample picture as an alternative of gauge unification. Okay. So before continuing, I emphasize a lot. So for the Yukawa and the coded coupling, you will have a pole at 15/2. And the U1 is always at 15/2. However, for non-abelian, it's at A equals 3. That's why this particular model has the potential to be asymptotically safe, because all the gauge coupling run into A equals 3, and it's already get frozen before the 15/2. That's why it's nothing will blow up, and everything will be asymptotically safe. Okay, so that's the key stuff behind it. So then it's like we choosing different kind of NF, and in principle you will have the fixed point. This is just showing you the two sample. So of course all these it's not a random, and they need to satisfy this vacuum stability condition for this quadratic coupling. Otherwise the potential is unbounded from below. Okay. For each of the whatever the choose of the fixed point, and so we categorize it into the irrelevant and the relevant. So the relevant coupling in the sense of the coupling, whatever the relevant coupling are the real the free degree freedom. So it's whatever you choose at an infrared, it will run into the fixed point. However, the irrelevant you don't have the freedom. So basically, you can see that's why in the series side, it's built this relevant coupling. They are the degree freedom which were expanding into this critical surface. So these are the real degrees of freedom. So this is you can see. So that's why actually asymptotic safety, you can see it a constant. It has a super strong predictive power at the infrared. That's why it's also very interesting to the phenomenology. You can see because there's so few relevant coupling, which means the dimension of the critical surface is so small compared with the total number of couplings. So there's not that much degree freedom, because all the arch flow start from UV fixed point. You need to align this critical surface. So it's not the freedom are very few. That's on the other side. It means it's super predictive at the infrared. You start from UV fixed point. It's only a very small RG range of RG flow you can play, which can go into the infrared. Then to matching the standard model will even narrow further. So it's a very strong predictive power in this picture. Okay. So I continue. So this is basically showing a few samples of how these coupling can running. None of these are the real to matching the standard model, but I will show that the one matching standard model later on. But these are just some sample for choosing the NF, and this Yukawa can running, and can see also this is for the quadratic coupling. There's a lambda. Actually, now they don't run that much. This is the other issue, because when you're choosing sufficient large NF, they don't run that much. But however, if you're choosing small NF, they will run a bit more. So this is how much they run is connected to the NF you choose. Okay. And this is for lambda R1, and lambda is another kind of the two quadratic coupling running. So this is the important. So you're starting from a UV fixed point, which is everything's safe. You're choosing NF. Then you need to go in from UV to IR and to running along the critical surface, and then it's go into IR. Then after symmetry breaking, partition symmetry breaking, eventually you need to matching the standard model for both the couplings and the Higgs mass. That's the bottom line you need to match it. So for example, here we need to match the top Yukawa couplings. So which may in our notation is around 0.66. So we can show actually there's very few points can really match in the standard model. It's really super strong predictive power. So we can show that by choosing this kind of type of value of NF, and you can roughly match in this top Yukawa. Okay. Then it's for the Higgs mass. It's this bio doublet become the two Higgs doublet after partition symmetry breaking, and so this is the matching condition between the bio doublet and the two Higgs doublet. Okay, then you construct the neutron, the mass matrices, and the eigenvalue of the matrices one at least needs to be 125. It's already confirmed by the experiment, and the other one in principle needs to be larger. So either larger than the 500 GeV or something like that. Okay. So this is something we need to match. So this actually further constrain the coupling of this quadratic coupling. So we can show it's by choosing this kind of NF copies, you can have this quadratic coupling, and this set of quadratic coupling can roughly matching this Higgs with 125. And by the way, when you're choosing this, you have one more free parameter you can play it in the 2D doublet model. It's this M12 parameters. So basically, some point is that this Higgs will run into 125 and it's frozen, and it's not running anymore. And when choosing this M12, and then you increase M12 more, you can make this MH2 get into much larger. So I think the current bound is roughly 500 GB. It's definitely can reach for M12 roughly 200 GB. You can realize that. Okay. And with this of choice, and you can have the topic color, which is also match. So, and another interesting is we also have a actually constraint we found is the Patis-Lam symmetry breaking scale. It's at least needs to be roughly like a 10,000 TeV. If it's too small, and we will find that the Higgs mass is always smaller than 125 GB. This is also a constraint we found is the constraint for the Patis-Lam symmetry breaking scale. You can see it's really, we don't have that much freedom you can turn into really matching everything, and you have a UV fixed point. This picture is very neat, actually very clean. So okay, so actually for trinification model, so I don't want to say too much, but I do want to show the scanning. So you can see it's we show it's the same as like Patis-Lam. We choose so many copies, right? And you can see it's only all these yellow are not viable. They have the UV fixed point, and you run into the IR, but they never match in standard model. And only this black point they can roughly match in the standard model. You can see how strong the constraint that the asymptotic safety or provides on these on the couplets. So it really helps you select. So if in a phenomenology you want certain motivation, and really the asymptotic safety helps you select the range of the parameter space, narrow down a lot, actually pin down a lot of the parameter space. Okay, so conclusion so far. Hopefully I already convinced you, and so the asymptotic safe standard model is feasible through the grand unified embedding with a large number of flavors. Okay, and the U1 problem, of course, is addressed because it's, the U1 is already embedded into the non-beam group and become asymptotically safe at the UV. And also, I hope I already convinced you, and the requirement of safety at the UV has a very strong predictive power at the infrared, and both Patis-Lam and the trinification can roughly match in the standard model at the infrared. Okay. Oh, yes, go ahead.
Okay. So is it possible to test this proposal on colliders, say LHC?
It's a super interesting question. For Patis-Lam, you know, it's a bit difficult because of the because it's at 10,000 TeV. It's a bit difficult, honestly. But some point, I think in the long future, actually this is also important. I think Yao Center, the particular Yao is strongly supported the future collider in China. For 100 TeV collider, there's a chance actually so just forget about everything. You think of that. So far, the SU3 is going to asymptotic free, right? Everyone believes this, but is that really true? In this picture, it's not necessarily true because the SU3 can first going down, and some point and then can going up. It's at maybe certain, for example, 20 TeV. This beyond LC. There's a chance for China to really find this if we rebuild this collider. Okay, so this is one thing. But the other also to test the phenomenology, this exactly relates to what I want to do. It's how to test it. So far we found a way which is simpler than this, simpler than collider, but through the gravitational wave. So this is also super interesting. So there are actually list that in principle there's 3 ways. So the first, of course, is this is even more direct. It's the safe directly through to test it on the lattice. Actually, so far it's in the this is Francesco Signor, my boss, and with the Helsinki group, and they actually they are so unfortunately they are not reaching. So you can see if you want something like this, right? But unfortunately, so far they cannot reach very far UV because it's expensive. So far they can do something reaching to this. They cannot go into that, unfortunately. So, but this is already a step towards a lattice to test this. Okay? The other way to, yes.
So strictly speaking, this is not yet a test because you
Yes.
didn't see the plateau yet. Okay.
Yes. Unfortunately, it's not because it's the cheapest to test is on the lattice, but it's still expensive because actually it's particularly expensive when introducing the more fermions, because as we already claimed, you need a very large number of flavors, and the adding flavor is expensive. Yes, but they are halfway to this level. And actually, I also discussed with Professor at Colorado. They have some other ways, but they also need funding in the States to make the further to this. So let's really hope. And the other is the kind that you already mentioned. And the third one is more direct, is in the gravitational wave through the partition. Okay. So I already mentioned a lot about the partition. So the interesting thing about partition, why it can connect to gravitational wave, because so you can imagine the frequency of the gravitational wave actually is connected to the energy, because we are focusing on the gravitational wave is through the first order phase transition. Basically, it's through the symmetry breaking of the Guts type theory of through whatever the model, right? And the higher the symmetry breaking scale and the higher the frequency of the gravitational wave. Actually, that's why it's very interesting for partition, because partition is roughly 1,000 dB to 10,000 dB, for example. And this will correspond to the frequency in the gravitational wave from 10 to 100, and maybe hundreds of hertz. So this is interesting because this is actually in the detection region of a LIGO. In the future, it's the LIGO voyage. So this is extremely interesting because if you have a much higher, like a SU5 gut theory, then it's beyond the region of the gravitational wave detection. Okay, and also it's particularly interesting. And people now, most of the people, they are focusing on the LISA because it's electroweak symmetry breaking. But actually, very few papers are really focusing on this. But it's growing. I know it's for example, in Germany, and also a few groups, they are really now is trying to pushing this high frequency gravitational wave collide. In the future, I think that's the one, maybe not to SU5, not 10 to the 15 GeV, but there's a chance in the maybe to 10 to the 9, 10 to the 10 GeV in the future from the gravitational wave perspective. So I think it's a very interesting direction. Okay. So I cannot go into too detail, but it's so for the scalar sector, to realize partition symmetry breaking is through this phi-r field. So this is the potential basically, and so basically we calculate everything. So from the tree level, the one loop level, common one type of potential, and the finite temperature contribution, and this is the ring and the daisy diagrams. Okay. So you need to include everything, and you have the full potential. And then it's like for this is the very nice thing of the safety. So if you have safety, and it only have a few set of the coupling which will be viable, right, to matching the STEM model. So we for example, we test one of them. You can see it realized the first order phase transition because you have a bump here. Okay. Actually, the other very interesting, as I don't have time to mention, is we found it's this strong first order phase transition. It's very connected, closely connected to a common Weinberg type of symmetry breaking. So we found that if you do not have a common Weinberg type of symmetry breaking, and it's very likely it's not the first order. So this is something we found also very interesting. Okay, and this is we using this kind of stream plot and to show this common Weinberg time symmetry breaking. So basically, you start from the UV fixed point here, and if you can toward this after this boundary toward this green line, it's symmetry breaking. So we just scanning this. Basically, this is the parameter space. This part is the parameter space which will work to have common Weinberg. Then you will have the first order phase transition. the picture is very beautiful. You start from UV fix. So actually it's really dynamical. You start from UV fix point and you're running the RG flow. And the common one, the time signature breaking, but there's no mass turn. It's dynamically tell you when it will have the signature breaking. And then you because of signature breaking, it triggers a gravitational wave and first order phase transition. So the picture is actually very beautiful, and you do not have too many parameters you can play compared with the pure phenomenology work. Okay. So this is the final result for this gravitational wave, and you can see as this is the red line. The red line is the signal from the safety. That's the way where the safety will predict it. And of course, if you break the safety, you will have other kind of lines. Okay, and the interesting, the safety lines will be you see in the detection region of this LIGO voyage. Of course, also in the very future Einstein telescope and the cosmic explorer. The LIGO voyage will be 2030, but because of the COVID, it will delay a few years, but it's promising. Okay, so this will be the first the first kind of you see the detection which can really detect and test the gut type theory and including the safety. Okay. So we have time limitation, but I try to move in faster. So now we from the large NF to the large Q. So these are actually the formalism. It's very similar. It's with all both of them with a kind of summation functions, and for NF and 1 over Q. However, it's also for both of them, actually, it's you will find a subset of diagram you can sum up. For the NF, we call the bubble diagram, and for the Q, and there's people in the spin group they call a frog diagram because it looks like a frog. But here is we take for this large Q, we take the Rattasi approach, which is basically is built upon the earlier Robokov and the TD Sun. It's a semi-classical computation, which is easier than this the bubble diagram summation approach. Okay. So basically, I will try to review the Rattasi approach in the next 15 minutes. Okay. So this is another thing kind of connected to I think interesting to the Yao Center. This is also connected to the future collider. Okay, so some people call this a Higgs explosion, but also maybe Higgs explosion. There's a multiple name. So basically, the idea is like this: the Robokov first proposed is that the multi-particle production process that's a problem. So basically, from the tree level computation, the tree level in the sense of here. Okay. So this black bulb is actually contains these polygons. So there's a loop inside this black dot. But after that, the Higgs this is the 1 to n. Basically, this is the 1 to n decay process. This is the tree level. So far, the tree level part they can be rigorously calculated by Robokov and Dickinson basically. And they found it's problematic because it will be blow up. It's because there's a factorial growth, so it will blow up. So that's become very serious. So it's also interesting in the future collider because actually Jose in Durham he basically estimate for this process it's the theory will be blow up around 130 Higgses, and if at the 100 TeV collider. So which means it's become a serious problem, both in the theory and also phenomenology in the collider physics. And Jose, basically, I think in the community that we now believe we don't think it will blow up, right? Nothing will really blow up. However, there's a very strong possibility. This, if we probably have a summation, and it is possible it's the Higgs, the production process will be increased a lot. So far, if you ask a collider physicist, they do not do this kind of summation. Phenomenologists, they will say it's the multi-Higgs production in the future collider is suppressed a lot. However, you see, this is a key difference signature. We believe if, in principle, if you have a proper summation, it will not blow up, but it will increase, not suppress a lot, but increase a lot, but never blow up. So it will become very important and interesting signature in the 100 TeV collider. This is really something we can see testing the theory and the phenomenology part. However, the theory, unfortunately, the theory that's I would say it's not fully developed. That's the key. Rattazzi is the first basically, and of course starting with Robakov 20 years ago, and they trying to push this direction on the theory side. Okay, I go into a bit further. So this is should be clearly is the Robakov and DT-Sun, they only have this this basically the tree level amplitude. So far from the tree level amplitude, and it's the cross section will be blown up by this factorial. Okay, and however of course you can think about whether this loop correction, what will happen for this loop correction. It's even worse, because for large number of you can see large number of scalar produced, it's the lambda n squared become very large. Then the one loop contributions could be even bigger than the tree level. It's even more problematic. So you really need a kind of a summation behind it to address this issue, right? And so this is the Robakov's insight. So he basically assuming that the cross section will be something like this. So we already see something very similar to this one of NF, right? We have a summation closed form. In principle, we should have a closed form function, and with this kind of summation. Of course, the interesting is for the one of NF bubble diagram, you have a pole, which may not be necessary here, but you need a summation function. And unfortunately, so far we only know the only known thing is the tree. It's the tree level contribution in this summation function. It's basically become this logarithmic part. Okay, and a few random terms, and you can see that we don't even know the B. So it's the loop contribution is completely unknown. So how to obtain this? We call it a holy grail summation function. So it's if we can obtain F, and we really can solve this Higgs explosion problem. Okay, so this is important. And Rattazzi basically he claims, since we cannot at one step to obtain this holy grail function, but however it is possible maybe we focusing on simpler problems first. So why not we, for example, calculate a scaling dimension of a certain fixed charge operator. So you can see that, for example, he proposed that in this U1 model, right? And in principle, the U1 model, the scaling dimension of the phi n operator, you can be rearranged like this. This is the leading order in the charge expansion, and this is the next leading, and this is a high order. And so you can see there's some essential similar in the formalism, but it's of course this scaling dimension calculation is much simpler compared with the cross section, but it is some way towards the real cross section. That's Rattazzi's proposal, and both of them, I think in the community we do agree. Well, let's start with something simple. So this is the U1. Okay. So I just show the procedure how to using the semi-classical computation to calculate the scaling dimension of certain we call fixed charge operator. Okay. You need a global symmetry to charge this your operator. Okay. So the first thing, I think everyone here basically familiar with this, but the first thing is we need to use this the power of this fixed point. So of course you can do Wilson-Fisher. We do Wilson-Fisher. We can also do Banks-Arcs. We can even do our UVC fixed point, but that's a bit more difficult because it's not true fixed point. Okay, so we start with for very simple Wilson-Fisher fixed point. Okay, so then we can use the power of it, then perform a well map and to the cylinder. So basically we will have the state operator. After that, we will have the state operator correspondence, and thus the Dirichlet charge will correspond to the scaling dimension. And that's the time translation after mapped to the cylinder. Time translation will connect to the Hamiltonian. Basically, it's the energy. So that's why eventually we will have this. So on the cylinder, it's easy. We just need to calculate the state, calculate the energy. So instead of directly calculate the scaling dimension, that's the reason we need to do this map. Okay. Then how to obtain this energy? Okay. So this is the next step. And so basically, we calculate the expectation value. It's the expectation of this evolution operator. And then you will see the interesting is when if you in the limit t to the infinity, basically it's a project out the ground state energy. This is, I should say, this is very important because it project out the ground state energy, the lowest energies, which by the state operator correspondence, right? It will not correspond to any operator. It will correspond to the operator with the minimum classical scaling dimension. This is also key, which means that this phi n you cannot have a derivative. When you have a derivative, it's become a more excited state. Okay, so this is something. So the next after that is the step is more it's more normal, I think. So basically, you're introducing a polar coordinates and into this the effective actions. Here I should be careful. Is the this boundary term is important. You really cannot ignore it. If you get rid of it, the final result is not right. And this boundary term actually is connected to the total charge. So it's the total charge is the n. It's because it's a phi to the n operator. It's the total U1 charge. Okay. Then from the effect actions, you will have the equation of motion. So this is the procedure. So first you have this equation of motion, and it's natural to assume this stationary configuration. So this F is basically a symmetry breaking vector. Okay, and then you can choosing this mu is the chemical potential. So this is a stationary configuration. Then you input this stationary configuration into the equation of motion. Then you will have these two. So this is the constant from the total charge, and which is the n. Okay. So then the next step is you input basically both the stationary configuration and this, and into the effective action you will obtain this part. Okay. So actually, let's say it's very simple to see how to solve it. Basically, the chemical potential encode. Now the chemical potential encode the lots of information. So you can see it's because here is the mu to the f squared. So you imagine you times the mu on here on this side, right? And you then will become mu to the third. And so it's become a mu to the third order equation, right? As a function of lambda and n. You can see it provides certain closed form. The chemical potential contains the lambda n with a closed form solution. The input this will provide you the leading order, the scaling dimension, or leading order ground state energy corresponds to the scaling dimension. Okay. So this is something we obtained for this closed form. We also call this F to be consistently all in the talk. And so the interesting is for example, you can see what is the structure, look like. You can do the expansion of the small top of the coupling and the expansion of a large top of the coupling. Here the top of the coupling is lambda times n. It's n is the chart instead of previously with the coupling times the nf. Okay. So you can see that basically this is become already very famous, starting with 2015 Orendo's paper, Orendo's 2 cents paper. And for large top of the coupling, you will have this kind of power law, and for small top of the coupling, you will have this kind of structure. Okay. So we move on to the next step as to how to calculate the next leading order contribution. And this next leading order contribution is basically it's contributed from the fluctuation. It's determined of this Gaussian interval. Basically, that's why it's the next leading order. After that, it's more difficult. You cannot easily obtain. That's why it's stopped at the next leading order, because it's because you can have this determined, and then after that you will become a summation of this is dispersion relations. So but beyond the next leading order is more difficult to calculate. So this omega I is the dispersion relations, And all the dispersion relations increase. For U1, it's very simple. But for more complicated model, the dispersion relation will become lots of different, right? And then the GI is the multiplicity of the each dispersion relation. You attain a certain weight because it depends on how many degree freedom you will have. So after that, because here it's very complicated procedure. I show it's very simple, but actually it's not that simple. Okay, then then eventually if you calculate all these, and you will obtain this. This is basically it's the form. Okay, for the small, because I could not show the whole closed form. It's a very complicated. Then for I just expanded it, it's become a simpler. And in the large limit, you will have the log form and the times this to hold the coupling with this kind of power. And the alpha beta, of course, it's calculated inside this calculation. Okay. So the next step is this what we have done. So you can see because of rotative, we want to connect this to the Higgs explosion, but you want still far away. So the very naive things to thinking of is how to from abelian to the non-abelian. And the simplest non-abelian case is the ON. So I think this is a very natural step. But actually, even still, the result actually can surprise a lot because the ON already been calculated by all different perspectives, right? In condensed matter and in high energy physics, and it's a high up to very high loop order. And actually also recently, and Jack Jones and in Liverpool, he is the very famous people in the calculation area. He also performed this ON check with our paper, and everything is consistent. And okay, so I will go into more carefully what is the lowest lying operating ON slightly later on. But here is basically we just bring the name. It's basically the Q index traces symmetric tensor operators. Right? Then you can have this calculate the scaling dimension of this lowest lying operators, and you can see the result. The result is for each epsilon order, and the leading order provides basically it's the leading Q, the largest Q, and the next leading order will provide this Q, the next larger Q contribution. So at each increase by at each, it's because here I can only show up to the 3 loop. Actually, it's the infinity order. It's very clear because it's for any it's encoded in infinity high loop order information basically. But only for the Q largest Q and the next larger Q. I think it's clear. And very interesting, all these results are consistent with the conventional perturbation theory result. So it is confirmed. Even we expected so, but when we saw this completely consistent with the conventional perturbation theory, we are still very surprised. Actually, it's so this is some very interesting feeling. Okay. So the big obstacles from abelian to non-abelian, there are actually the two interesting questions related. And so what is the lowest lying operator? Because it's I should say that the vacuum expectation value for the evolution operator, right, from T to the infinity, is always the lowest energy state, and then it corresponds to lowest lying operator with the lowest classical scaling dimension. So what is the lowest lying operator for all different kind of model? This is always the question we need to ask. And for U1, it's simple because you don't have too much you can construct. It's over phi n. But for ON, it's slightly more complicated, but it's still not that complicated. But for more complicated model, this is a difficult question we need to ask. What is the lowest lying operator? And the other thing is for what is the charge configuration? Right? It's not for U1. You only have a charge, and it's also very trivial. That's why Rahati is smart. He doing the simplest case, but there's these two subtleties never occurred in the U1, but in non-abelian theory, more common non-abelian theories, it occurs very often. Okay. this we actually made further progress when we playing with this UN linear sigma model. So I would start to highlight a few the charge configuration. So I already mentioned the U1 model, there's no charge configuration because there's only charge, that's it. And for the ON, you do have a charge configuration. However, because of the symmetry, it's only the total charge matters, which means whatever the internal charge configuration, if the total charge is the same, then it's the result of the scaling dimension basically is degenerate. So it's clear from here. You can choosing, for example, as this kind of a general charge configuration, and but you can see because of the ON operator, eventually basically it's a sum up of this MI. That's the thing really matters. So it's only the total charge matters in ON. However, this is not true for the UN series. Just a step from the simplest to more and more complicated case. Okay.
Well, actually, so, you're running out of time, so can you wrap up?
Yes. So basically, just showing one minute. This we provide the basic charge configuration recipe. Eventually, the conclusion is we can identify the representation of a fixed charge operator. So basically, you input a charge configuration, and it is possible we obtain to this because you will have a multiple kind of representation. Then which representation corresponds to the operator with this choice of charge configuration? We are able to identify this in this most recent paper. Basically, it's put out this week. Okay. So this is the result. We can calculate this. We show actually multiple more complicated example, but in this talk I show the simplest case. Okay. So basically that's the conclusion. So for the asymptotic safety part, so I hope I will convince you that by using the large NF techniques, this U1 long output problem is addressed. Okay, and both partition and trinification can roughly match in the standard model at infrared. And because of the strong first order phase transition, we can using gravitational wave to test this safe partition framework. And then it's combining the semi-classical computation with the CFT. And for the large charge case, we can calculate the scaling dimension of a class of fixed charge operators up to next leading order. Because beyond that, we do not have this determinant. It's not easy to solve beyond the next leading order in the chart, but it's encode infinity high loop order information. It's like a large NF, right? Basically it's a summation functions. And we also create a recipe. This is something I think the key progress beyond the Ratazzi is we really get into what is the operators, what is the fixed charge operators, what's the representation connected to a chosen of the charge configuration. In particularly, what we get into the importance, make people notice what is the charge, how the key role of this charge configuration. I think that's something never realized in the Ratazzi paper. Okay. So last things I think is important for Yeltsin is this multi-fixed production is really important for the future 100 TeV collider. So our work is it's not a cross-section yet, but it is a one step towards this holy grail summation functions. So we hope at some point, because we are now really trying to move closer and closer to the standard model from U1 to ON, UN, and then actually the next step we are considering is adding fermions. How to adding fermions to play with the operator. So it's to making closer and closer to the real standard model situation. So that's just this explosion as a long goal. It will take a few years. It's not a finishing one, but it's a long goal, and it's promising to us. So thanks.
Yeah, thank you very much. Is there any question? Then please unmute yourself.
I have two naive questions.
Yes.
Thanks for the nice talk. The first question is that as far as I understand, asymptotic safety is a program to whose grand goal is to solve the normalization of quantum gravity. Do you have anything to say about that?
Yes. Actually, this is the final goal because the at the beginning is basic asymptotic safety was proposed by Steven Weinberg in 40 years ago in the gravity paradigm. However, actually now it's I think it's gaining some momentum after the functional RG is in areas they developed, and I think people. So actually there are two. Now it's two groups working on asymptotic safety. So one is asymptotic safety without gravity. This is me, Francesco, and as most of CP3 group and the people connected to CP3. And there's also a gravity asymptotic safety gravity group. So it's for example Heidelberg group in Europe, and also CISA, and they working on that. So it's a parallel paradigm. And in this without gravity paradigm, we actually do think in the next step also to adding the gravity contribution into this into the beta function to see how it changes. However, there's something very subtle I should say is for example, it's very interesting. It's there are papers that for example adding the gravity into the gauge beta functions, and some people claim the contribution is negative. Some people claim the contribution is zero, and some people claim the contribution is positive. Actually, different people actually eventually give very different results. So this is issue really needs to look into. And actually, and the lithium in success he proposed, it is possible the calculation so far is not convinced to take in the gravity into account, and it's regulator dependent. So So it's choosing different kind of regulators. You will have a different contribution, but as a negative and as zero and a positive.
This is a problem, right? Because the contribution should not depend on the regularization scheme.
Yeah, in principle it should not. But however, actually so far what they found is become when you're adding the gravity contribution, it's the result can be totally different. Actually, all positive, zero, and negative existing in the literature. It's so I think this is something we need to look into. And also it's very important to make a unified paradigm including gravity. I totally agree. This is an important direction.
Okay, thanks. And my second and other question is probably I did not understand fully, but you motivated your talk in the beginning by saying that UV theory has the problem of a Landau pole because it's not asymptotic free in the UV, right?
Yes.
The U1 coupling. So and then you said this could be solved by asymptotic safety by introducing large number of fermions. Yeah. But then in the middle, you also said that this is not enough, and you have to embed U1 into a non-abelian gauge group. But if it is non-abelian, it's already asymptotic free. Why do you still need a large NF?
Yes, this is also a good point. So it is true. So then it depends on whether you can definitely embed in U1 and into grand unified sleeve, and then everything you need to make sure everything asymptotic free. So not the gauge coupling. You need also make sure the Cordy coupling, Yukawa, and all of them are asymptotic free. Actually, this is also we actually also played. This is also not easy to realize. But however, there's an alternative, assuming they can realize. But this is a one picture. So everything asymptotically free, all the coupling, not just the gauge coupling. And assuming this can be realized, there's also a parallel, right? We can imagine that in the UV, it's not necessarily asymptotic free. It's not necessarily Gaussian fixed point. It can also be a UV safer. So we do motivate ourselves to addressing the purely U1 Landau problem, but eventually we are moving into the grand unified type, but it's not asymptotic free. Grand unified, asymptotically safe grand unified. Yes. So
thank you very much.
Starting the motivation, but evolve because of the lots of subtle things that happens. Yes.
Okay, thanks. Thanks a lot.
Yeah.
Okay, since the time is running out, I want to stop here and then let's thank the speaker again. Now I stop recording.